everyone. Thank you for joining AWM Pitt Grad Seminar. Today we have two speakers. Our first speaker is Vaishavi Sharma and second speaker is Remjim Tomar. Vaishavi is from Tulane University. Her topic today is arithmetic properties of divisor function, and Remjim is from Czech Academy of Sciences. Her topic is the neural coding problem and the role of instantaneous firing rate. Vaishavi, you can go ahead.
All right. Thank you. And thank you again for this opportunity for this talk. Right. So I will be talking about the arithmetic properties of the divisor function. This is a chapter in my dissertation. I'm a student at Tulane University and I'm in my final year, so I'm getting ready to graduate. There we go. So first, I would like to acknowledge my collaborators. So Dr. Moll is my advisor, and he was a collaborator for this project. And then I also work with Diego and Dr. Amdeberhan, who are also at Tulane University. So to start, I will start with some definitions that the divisor function here is the sum of the divisors. It's a well-known arithmetic function denoted by a sigma of n. And it's the sum of all the positive divisors of n, including n. So I have some examples. Whenever you take the sigma of a prime number, it's just p plus 1. And then I have a sigma of 9. We're adding the divisors 1, 3, and 9. And similarly for 6, we have 1, 2, 3, and 6. So we take that sum. So like I said, this is a well-known and well-studied arithmetic function. There are quite a few properties that you might have already seen about this function if you've seen this before. The first one is that it is a multiplicative function, meaning if you take the sigma of the product of two co-prime numbers, then it's the same as the product of the sigmas. This one is an interesting identity that was proven by Euler, that sigma n satisfies the following recurrence. Here you have the 3i squares plus and minus I over 2. These are the pentagonal numbers. And what's really interesting about this particular relation is that the partition numbers also satisfy a similar recurrence with just the initial conditions being slightly different. So this wasn't really expected, and it is a really cool identity. And here I have an example to show how it really works, even though the sum is infinite, but that's not really the case because in the end you'll end up with zeros. We also see the divisor function in modular forms. So here they show us the Fourier coefficients of the Eisenstein series, and using the finite dimension of the modular group, we can also show some really cool identities for different forms of the sigma function. So here, when you have sigma 7 and sigma 3, this means you're adding the powers of the divisors. So sigma 7 would be the 7th powers of all the divisors. Similarly, sigma 3 is the cubes of all the divisors, instead of just adding the divisors of n. And there's really no other way of proving a relationship like this other than the modular forms approach, which I find quite interesting because there's really no intuition behind this. All right. The last thing I have here is just a plot of sigma n. As you can see, it has like a really interesting growth pattern. There's also a cool connection between the Riemann hypothesis and the bound on sigma n with the harmonic numbers, which was recently proven by Dr. Lagares. So my work actually concerns with the divisibility of these divisor functions. So when I talk about the prime divisibility, one way of looking at that is using the p-adic valuations. The p-adic valuation of an integer is the highest power of that prime that divides that integer. And we can extend this to rationals by taking the difference of the p-adic valuation of the numerator and the denominator. And then by convention, we set the p-adic valuation of 0 to be infinity. So here I have some examples to clarify that more. So since 12 is 4 times 3 and 4 is 2 squared, so you have the 2 valuation of 12 is 2. And then the 7 valuation of negative 14. So the negative sign really doesn't play a role here. So it's just 7 times 2. So it's just going to be 1, the valuation. And then for a fraction, you just take the 5 valuation of 3 minus the 5 valuation of 10. So my dissertation is concerned with finding the periodic valuations of sequences. So in this case, we're looking at the divisor function, and we want to study the sequence that we obtain by taking the periodic valuation. And we look at either a closed form or a tree structure or error terms, etc. So we want to study the structure of these periodic valuations. Here I have a motivating example for these studies. This is a closed form formula given by Legendre for the periodic valuation of n factorial. And as you can see that this form that we get is involving the integer itself. So you don't really need to take the product anymore. You don't have to simplify the factorial at all. You just need n, and SP of n is the sum of the digits in base p of that expansion. And then your denominator is just p minus 1. So if you have to calculate, say, the periodic valuation of 10 factorial, we just get 10 minus 2, and your denominator is just 1. And this closed form also tells us the asymptotic behavior of the periodic valuation of n factorial, and that it is closer to n over p minus 1. So, all right, so sorry about that. So what can we say about the periodic valuation of sigma n? One of the things that is, again, just another well-known result or a property that we often come across in elementary number theory is that sigma n is odd if and only if n is of this form. So it's either an even number times a squared. So using this, we wanted to study what can we say about the periodic valuation of any other number. So we found a closed form solution for the periodic valuation of sigma of a power of prime. And finding it just for a power of prime is enough because sigma is a multiplicative function. So we can extend it to any integer. So yeah, here we have a nice closed form formula for this periodic valuation. And now we want to see what does that look like. And this is the plot that we get. So the blue lines are the periodic valuations of sigma n. And we were trying to find a bound for it. And the yellow line that you see, which is a nice bound, is the ceiling of log 2 of n. And when we were trying to prove this and to actually see what these numbers are, where this bound is attained, we found a very nice connection with Mersenne primes. So Mersenne primes are primes of the form 2 to the n minus 1. And we have a really cool result here, which shows that the inequality always holds, and we get equality if and only if n is the product of distinct Mersenne primes. And it's pretty interesting, and this actually comes just from the inequalities involving this floor and the ceiling function. But anytime you have a non-distinct Mersenne prime, so anytime that repeats, we can actually bound it by the floor function. All right, so this was for 2, and it's always nice to do these things for p equal to 2 first, because that's the only even prime. And now we want to generalize this to the odd prime case. So once again, we were able to find like a nice closed form formula for the odd prime. And here Q is any prime, and R is the order of Q in ZP. So we get another nice relation between, a nice closed form formula based on the relation between P and Q, or how Q is in ZP. And we wanted to extend that and say again, what can we say about the bounds? Sorry. All right, so here's the picture that we have, and this one's not as nice. So again, with 2, we see that the bounds are being attained, but as our prime increases, the bounds, it's very rare that that happens. So this looked really interesting, and we were curious to see if this was even a good bound or what we should try. And what we saw is that when we look at the equality, meaning when the bound is attained, these are actually solutions to the Ungren-Nagel Diophantine equation of this form. And based on what is known of these Diophantine equations, there's only a few prime solutions, because again, what we're looking for is for solutions when x and y are prime. And this is exactly why we don't get the equality as much. So yeah, this was a cool connection that we found between these bounds and a Diophantine equation. And then if you see in this case, if you make x is equal to 2, then you get Mersenne primes as well. So these are all like nicely interlinked things that we got. So based on that, we have a theorem for when the p-adic valuation can be bounded by the ceiling of the log function. But again, this isn't true for all values of n because of the relation with the Diophantine equations. We have these three conditions that an integer must have. But at the same time, because of what is known about the Diophantine equations, we have a conjecture saying that this actually holds for every n. So the third condition that we have, we ran it up to, I think, 1 million, and we could not find any examples. For the first two cases, it's very easy to find examples of P and Q where this works. But for the third one, we didn't find any. And again, this is mostly computational stuff. So just based on that, well, we have a conjecture saying that there is no integer where that happens, and that this bound holds for every integer n. Okay. Last thing I have is some corollary from the result, the closed form that I showed you earlier. And we're going to apply that formula to find integers n when the triadic valuation is 0. So we're looking for values of n where 3 doesn't divide sigma of n. So this is kind of similar to what the first result we saw for 2, right? And we see that n would be of this particular form where you have restrictions on the powers based on the number being 0, 1, or 2 mod 3. I just have a quick outline of the proof for this. So as you can see, when your prime is 3, the only options for Q would be 1 or 2 mod 3. And based on that, the order can only be 1 or 2. So we have these nice restrictions, and then we can just apply it into the closed form formula that we have. And rewrite the prime factorization in this form. And that's exactly what the previous formula was. All right, so this is almost the end of my talk. Some of the future work related with this project is to investigate similar results for larger primes. This was a cool result that we noticed, was that we found when sigma n is congruent to 5, meaning when it's non-zero, the 5 valuation is non-zero, we found an interesting sequence of integers. And I don't know if so there's a website called OEIS, which is an encyclopedia of integer sequences. And this sequence appears on the OEIS just as this. There's no other description for the sequence, or there's no other reason why the sequence appears in this case. So that would be really cool to study and explain why this is happening and what's so special about these numbers. And then it would be nice to find some p-adic valuations for sigma k of n, where again k would be the kth power of the divisor. These are some of the references that I used, and that's it. Thank you.
Thank you so much for your talk.